Good morning. Great to be with everybody. Appreciate everyone taking the time to be with us today. Just a quick introduction to my background. So I work in the Azure HPC global team. I work as part of a team of architects, HPC architects. We work with some of the larger Azure HPC customers who have a sort of HPC centric workload, and so we guide and help them to get the most out of Azure. So in the next couple of slides, I would like to build on the Azure HPC material that Mark presented, and the preceding slides talk specifically about how we can use those Azure building blocks that he talked about with our customers to create solutions for some of specifically the oil and gas computational and storage challenges. So what we're looking at here is the complete oil and gas workflow process. It is very complex, but it can be broadly divided into three sectors or categories: upstream, and we have midstream and downstream. Today, we're going to be focusing on the oil and stream, or the oil and gas upstream processing, primarily because of its large HPC compute and storage requirements. If you go to the next one, Mark, please. So the three key application areas in upstream processing are seismic processing, we have reservoir simulation, and remote visualization. And we see more and more applications of AI in this space as well. Seismic processing involves, first, as you know, the collection of huge amounts of raw seismic data, filtering and cleaning the data, and then using various numerical algorithms such as reverse time migration, full wave inversion, to generate detailed 3D subsurface images that geologists and geophysicists can interpret to determine if hydrocarbons are present, and of course in what quantity. You know, seismic processing itself accounts for over 70% of the HPC cycles. And generally large parallel file systems like Lustre are used to handle the large I/O requirements. For these applications, we see a mixture of in-house and commercial seismic processing applications. In regards to communication, MPI is the primary layer of communication for these applications. Although in many cases, not really needed, because often a single shot is computed on its own single node, and many shots need to be processed in parallel, which is really a description of an embarrassing parallel problem. These applications, specifically seismic processing applications, they're very floating point intensive, and so they also perform well on GPUs if they are supported. Now, as we kind of move over to the reservoir simulation type codes, reservoir simulations are utilized in the development and planning of oil field production. It is used to understand the flow of oil, gas, and water to help determine an optimal and safe location to drill and manage the oil production over time. The compute and storage requirements are not quite as high in this case as seismic processing, but it is often preferred in this space, or this suite of applications, that Windows and Linux compute nodes have access to the same storage, so you can kind of reduce that extra copy overhead. Reservoir simulations like seismic processing typically use MPI for communication. And in this particular case, a low network bandwidth a high bandwidth and low latency network, like, for example, InfiniBand, really helps with parallel scaling. And as Mark pointed out, we are sort of unique in that space, that we have those SKUs that support and have InfiniBand. Responsive remote visualization is critical in all aspects of the upstream workflow. It really allows the geophysicists to review the 3D subsurface images generated from seismic processing. It allows them to share and collaborate with colleagues, set up and review results from reservoir simulations. And we see AI being applied to new areas in this space, such as using I/O edge data and drone images to develop deep learning models using predictive maintenance. If you go to the next slide, please, Mark. We understand that our oil and gas customers, they rely on several commercial applications and are a key part of their workflow. We work closely in partnership with oil and gas ISVs to make sure that their frameworks, applications, and solutions work optimally in Azure. And we can see, a couple of examples that we've highlighted here. If Mark, you go to the next slide, please. Here's an example of one of our oil and gas customer successes in Azure. We worked with Repsol migrating their on-premises reservoir simulation environments to Azure. The performance and flexibility of their cloud solution in Azure resulted in a cost-effective solution, allowing them to make time-critical decisions much faster than they did before, which really gave them a competitive advantage in this space. Next slide, please, Mark. So in this particular slide, I want to really dive in and spend some time on this particular slide. The reference architecture for seismic processing and reservoir simulation, they have similar components, but there are a few differences that, as we kind of go through this slide, I'll point out as we go along. So let's start on the left-hand side and move to the right. The first question to be addressed is how users will access the cloud infrastructure. The options here will depend on your security policies and will dictate what restrictions and safeguards you need to put in place. We can control what ports are open using network security groups, authentication using Active Directory or LDAP. If you have restrictions that, for example, if no public IPs are allowed, we support those scenarios using Azure Bastion, in which access to a VM in Azure is only via the Azure portal. You can also have a private connection from on-premises to the cloud via ExpressRoute. And for remote visualization, we have a number of options ranging from third-party services, which Mark referred to, Azure Virtual Desktop, or popular third-party solutions. Solutions from HPE, for example, zCentral, Remote Boost, Mechdime, TGX, VMware, Horizon View, etc. All of these work well in Azure. So with the largest regional global footprint and a large selection of specialized visualization VMs, specifically the NV series, you'll be able to select the right visualization VM to give you the performance and interactive responsiveness you need. Now, talking a little bit about license servers, it is, it's fairly straightforward to set up and access a license server to support commercial applications on the same VNet. We see that in this chart here. To tap into Azure dynamic provisioning and auto-scaling capabilities, as Mark mentioned, we have two primary tools. We have Cycle Cloud and Azure Batch. Azure Batch can be considered in Azure more of a native scheduler, cloud native sort of, and it's often selected for SaaS solutions. Cycle Cloud is a more natural fit for dynamic cloud bursting capabilities, or if there's a preference with your user community to use one of the popular HPC job schedulers like PBS, Slurm, LSF, and we support many others as well. At this kind of stage of this sort of design of the architecture, you should consider what type of VMs you require. Do you need GPUs for running your RTM jobs? What type of compute VMs? Do you need InfiniBand? Will each shot run on a single VM, run on multiple VMs? And how much memory do you need? We have VMs to satisfy all of these requirements in Azure to optimize and minimize costs. Auto-scaling strategies and policies need to be considered based on the company's policies and maybe your typical or expected usage. For example, when to deallocate VMs? What is the maximum number of VMs to deploy? Do you want to keep a minimum number of VMs always up to reduce provisioning time if you need some more capacity? And in that particular case, auto scale to what maximum number of VMs? All these questions need to be addressed and answered to define the right architecture for your situation. Now let's kind of turn our attention to some of the storage considerations. For reservoir simulations, the I/O requirements are not quite as high as seismic processing, but do require storage solutions with lower latencies and modest capacities. Typically what we see is capacities maybe less than 1 TB is sort of sufficient for these type of applications. Reservoir simulation environments often require storage solutions that, as we talked about, that can handle dual protocols so that your Linux workstations or Linux compute nodes and Windows can access the same storage. For example, Linux maybe through NFS and through Windows through, for example, maybe SMB. Working with customers specifically on seismic or in reservoir simulations work, we have found that the Azure NetApp files work quite well as a primary storage solution. If Azure NetApp files is deployed in the same data center as compute clients, and we can control that proximity with things like proximity placement groups, which gives you that control, you can achieve a less than 1 millisecond latency for those sort of workloads. And for a single volume, it's possible in Azure NetApp files to get read performance on the order of 5 gigabytes per second and write in the order of about 1.5 gigabytes per second. And of course, you can have multiple volumes. Now, seismic processing, compute, and storage requirements, they can be significantly higher than reservoir simulations. Large oil and gas companies would have, thousands of HPC compute and hundreds of GPU nodes, and typically a large Lustre parallel file system to handle a huge capacity in the order of petabytes of data, and also to handle a large throughput. Typically, you might require a couple of 100 megabytes per compute node. And as you add more compute nodes, those storage requirements go up significantly. What we see is oil and gas companies may have, half a petabyte to a petabyte of data for active projects, but tens of petabytes of data for older projects on the Lustre parallel file system are just scattered and stored on archive tapes. In Azure, ClusterStor or an IaaS parallel file system are popular seismic processing storage solutions. ClusterStor, as Mark kind of talked about earlier, is a first-party solution using Cray hardware. I guess HPE technically today, it's Cray hardware hosted in Azure data centers. ClusterStor is a cost-effective solution for those storage scenarios that require at least a few petabytes of storage capacity and fairly large throughputs on the order of maybe at least 60 gigabytes per second. We can go much higher than that, but those, and in situations where you need a very high utilization. So you're constantly using your storage. That's a good fit and very cost-effective solution for ClusterStor. Now, if your I/O requirements are a little smaller, not as much, IaaS could be considered in those sort of scenarios where the I/O requirements aren't quite as high as ClusterStor. And also in situations or locations around the world, especially in oil and gas space, where you maybe were operating in a very challenging or remote location, ClusterStor may not be available. In those sort of scenarios, an IaaS-based parallel file system is a good fit. In order to provide more flexibility and help reduce the cost of your Lustre parallel file system, we provide a direct integration to Azure Blob Storage by Lustre Hierarchical Storage Management Interface, or otherwise known as HSM. This allowing you really to restore and back up all archive files to Blob Storage directly. So the size of your Lustre parallel file system, you can keep at a minimum to minimize those costs. On Azure Blob Storage, once you got your data over there, you can then store your data on different tiers. We have hot, we have cold, we have archive. And so that depending on how frequently you may need to access your data, This again helps to minimize data costs and have your data in the right location, providing a complete rounded solution. You know, Blob Storage on Azure also offers lifecycle management, which is sort of a rules-based policy to automatically transition your data between the different tiers. So that's something that you can set up to happen automatically in the background. So Mark, if you could go to the next slide, please. Yeah, this is one, yeah. So customers who are new to the cloud, you know, where they usually start is with a sort of hybrid architecture, where they can still use their existing on-premises HPC infrastructure, but also have a cloud burst or extension to the cloud capability for those times when they need that extra capacity. This architecture that we're looking at allows customers to use existing on-premises, maybe, for example, authentication with an Active Directory and license servers that they use on premises also in the cloud as well. How your on-premises infrastructure is connected to the cloud is important. It will impact security and ease of transferring data between the cloud and on-premises. As we talked about, the Azure Express route allows you to have a dedicated, private, high-speed network connection to Azure. Now, Cycle Cloud, when we start talking about the cloud bursting capability, Cycle Cloud can be integrated with your existing on-premises job scheduler to provide a cloud burst capability. It is possible in this hybrid architecture to use your existing on-premises storage by mounting it directly in the cloud. And for some applications, that may work fine. But depending on the location of the Azure data center, this may not work well for more latency sensitive applications or workloads. In such cases, it's better to have your data closer to the compute VMs in Azure. Now, Mark mentioned early on, he talked about HPC Cache. So fortunately, Azure has a solution for this, which is Azure HPC Cache. So the Azure HPC Cache allows you to connect to your on-premises network attached storage and presents it as an aggregate namespace. And it automatically caches the hot data to improve I/O performance and reduce latency. You can have, in Azure HPC Cache, you can have multiple backend storage options connected to Azure Cache, for example, like Blob Storage, and also presented as an aggregate storage space. HPC Cache is ideal for more read-heavy workloads. Some of the larger HPC Cache configurations can achieve expected throughput on the order of 8 gigabytes per second. So Azure Cache is not just only for hybrid scenarios. It can also be used for cloud-only scenarios. Let's say, for example, in Azure, you have Blob Storage and, for example, Azure NetApp files in one region, but you would like to access that data from a different region. HPC Cache is ideal for that sort of scenario as well. Okay, Mark, could we go to the next slide, please? So now, let's see some performance results that we've been able to achieve with the infrastructure that we mentioned in the previous slides. This slide shows the throughput results from running a large seismic processing benchmark using Shearwater Reveal RTM on Azure. The seismic data used was a SEG seam data set, but the data set, it was modified with the help of a customer, an oil and gas customer, to represent a realistic production size problem from a compute and I/O perspective. For this benchmark, we wanted to execute over 700 seismic shots concurrently, see how it scaled, and what was the variation in runtime for each seismic shot that was processed. For this particular test, an IaaS Luster parallel file system was built. So in the upper left bar chart, we can see the result from running various synthetic I/O benchmark tests with IOR, using different Luster tuning configuration and different I/O patterns. You can see we were able to achieve about 200 gigabytes per second of performance. And over on the upper right-hand side, While the seismic RTM benchmark was running, we recorded, you can see 213 gigabytes read performance using the Lustre LTOP performance monitoring tool. The bottom plot shows the result of running 726 seismic shots concurrently on 726 HB120 v2 VMs. These are our, which Mark mentioned, the AMD Rome CPUs. The horizontal axis in the lower chart shows the shot number, and the vertical axis shows the elapsed time. The results show that the variation elapsed time for all the seismic shots is within an acceptable range. It would be expected, given that we use an IaaS parallel file system, that if we use ClusterStor, the variation in elapse, the variation would be even less, and ClusterStor will be expected to be able to handle a much larger number of concurrent RTM jobs. If we go to the next slide, Mark. So this is an example of the type of collaboration we have with ISVs and partners to optimize their applications on Azure. We work with Shearwater and AMD to optimize the Reveal RTM on Azure, specifically on the HB120 v2 VM, which is the AMD Rome processor. On the left side is the HB-v2 NUMA topology. The HB-v2 has 30 NUMA domains depicted here. The latency between each of the NUMA domains is shown. So by carefully arranging the parallel processes and threads into optimal groups using this information, we were able to reduce the Reveal RTM elapsed time on the HB-v2 by about 40%. Next chart, Mark, please. Yeah, this story. Yeah, so this bar chart shows the IO performance throughput, the IO throughput performance for a 15 petabyte ClusterStor parallel file system in Azure. We use IO-OR to run the synthetic IO benchmark, and we're able to achieve about 240 gigabytes per second of IO throughput using 200 compute clients. This particular ClusterStor configuration has 18 scalable storage units. So which roughly comes out to, we were able to achieve roughly 13 gigabytes per second per SSU. And so for an L300, this is not a bad number, it's pretty good. On Azure, we can support much larger ClusterStor configurations than we benchmarked here. And up until now, we've kind of talked about a number of different storage solutions, specifically for oil and gas. I just want to mention that ClusterStor and the other storage solutions can be used in other energy applications and other verticals as well. If you can go to the next slide, Mark, please. Just a few words on the OSDU. So many oil and gas companies have been looking for solutions to improve their data management problem. There are many different data formats, often different formats for the same type of data. This has caused oil and gas companies to have these silos of the same type of data in different locations. Data often did not even have metadata, so sometimes it's difficult to tell what exactly the data is and to track the lineage of that data. An open data-centric platform was needed to solve these problems. Shell did some work on this issue and helped organize a community effort around this problem. And in 2018, the OSDU consortium was established, and Shell contributed its initial work to kickstart this effort, which represented R1. Schlumberger was also thinking about solving similar issues with its Delphi cloud platform. And Schlumberger likewise contributed its initial OSDU implementation to the OSDU consortium in 2018, and this represented release 2. Microsoft has been supportive and an active member of OSDU consortium from the beginning. You go to the next slide, please, Mark. So OSDU release R4 was released in kind of late 2020. So the OSDU continues to evolve, supporting more oil and gas data types and even expanding to support new energy data types and applications. We are also, because of the maturity of this frame, we're also working with partners and customers to make sure our implementation of OSD in Azure to meet and exceed our customers' expectations. If you quickly go to the next slide, please, Mark. So this is an example of the type of collaboration we are excited to be a part of, working with leading oil and gas service providers and key customers to be part of their true digital transformation in the cloud. If we go to the very last slide, please, Mark. So this is kind of the material that Mark and I wanted to present today. There are some additional resources here that you may find, links that you may find useful. If we have time, we can take, Mark and myself would be happy to take some questions, or please feel, if not, please feel, just reach out to Mark and myself at your convenience, and we'd be happy to help you out.